Okay, so this is, I guess, lesson 6, I think, technically. And if you're going to study a surface, right, we can just draw an arbitrary surface. This time I'll try to get my axes right. This is x. Maybe I'll draw the y-axis later, or I'll label it later too. So let's say you have this mound here, like that. Or so you could just draw some squiggly lines, sort of. From above, they would look parallel to the x-axis. Maybe some that go this way. Might have drawn too much there. Okay, so anyway, you can kind of round this off like this. And then I'll draw my y-axis poking out the back. So if you're not real good at drawing, it doesn't matter that much. The whole point is to understand what this lesson's about. So imagine a green point that is the highest point of all. Okay? So we're going to call it AB. Huh? King of the hill, right. So in this world, right, of 3D, which is really 2D, because you only pick your x and y, z is sort of already dictated. In this particular world, right, if I say a point is a relative max, AB is a rel max, what do I really mean by that? Do I mean that it has the biggest y value around? Because that's what it used to mean. Right? I don't think that's what it means anymore. I don't think it means that AB is a rel max. I don't think it means that it's the highest y value around. That's not what it means anymore. What does it mean? The highest z value around, right? Around where? That's an important question. What do you mean around? Well, I mean in its neighborhood. So you could draw like a little ring around that point, see? It's a rel max if plugging a and b into your z function gives you a value of z greater than or equal to all the other points in the region. So greater than or equal to z of xy for all xy points in the neighborhood. Okay, so that's a very colloquial word to be using, neighborhood. What do I mean by neighborhood? Well, the idea is I should be able to make my neighborhood as small as I want, okay? So that little ring I drew, I should be able to shrink it down to be like a 0.1 radius around the ring. And within that ring, I should not find any other candidates for absolute extrema, okay? So I might say, well, who's the oldest in this class, right? And two people raise their hands and say, well, we're 18 years old. It's like, oh, okay, well, that didn't really work. So then you'd like make it more fine-tuned. You say, okay, so who's the oldest 18-year-old, right? So what you're doing is you're narrowing the criteria and looking for that head honcho, the oldest in the class, right? By narrowing the criteria. So it's the same idea here. As you shrink the circle, you can really tell if Z is the highest point in its neighborhood. Now there might be other points near Z, near AB, that are contesting. They're like, no, we're the same height, we're the same height. But when you shrink in the neighborhood, make it small enough, right? You can find that Z is at least the king of some hill, even if it's a small one. So maybe my analogy wasn't too good. If I said, who's the oldest in this class? And two people raise their hands. So who's 18? Raise your hand. Okay, this is perfect, okay? So now what I'm going to do is I'm going to split the class. Okay? So now this side of the room, who's the tallest? Who's the oldest? Hunter. And then on this side of the room, who's the oldest? See, we've got two rel maxes. See? Two relative maxes. But I had to make the circle smaller. I had to find a neighborhood where Hunter was the oldest. I knew he was the oldest of some group, right? The same thing's happening here. Okay, so rel max is exactly what you think. It's the biggest Z value. Okay? So what happens at a point like this? What happens at a point like this? What happens to the slope or the rises and falls of the hill on any blue line? What's the slope of the tangent line if you're looking at blue curves? Zero, correct. In other words, dz dx is 0. And what, if this truly is a peak, what is the slope of the tangent line on one of the red curves? Zero, correct. So if a point is going to be considered a rel max, it needs to have one of the following two properties. Okay? Well, it needs to have both partial derivatives being 0. These both have to be 0. Okay, or there's another possibility. dz dx, that should be a partial derivative, and or dz dy is undefined. Okay, here's what I'm talking about. If you're at the top of a smooth hill, you can say something about the slopes at your feet. You can say that the ddx and the ddy are both 0. There are hills, though, that don't have a sharp, do not have a rounded off-looking peak, you know. So this reminds me of my younger years when I used to go to a skateboard park called Sadlands in Anaheim, okay? And they had these volcano things like this. They're just made of concrete. And you could just ride up them. It was so fun. They were a little narrow at the top. Imagine if they were coming straight up to a point, right? Imagine if all these curves just met together to make a cusp, right? That point would be the absolute max, probably. Definitely a relative max, you see. But there wouldn't be any slopes there at all. Does that make sense?
Are you referring to Brookhurst?
Brookhurst Park used to be a skate park.
There's still one there, but they don't call it Sadlands.
It used to be called Sadlands, and then because of liability reasons, they went through and sprayed this chunky stucco stuff all over the ground. Trust me.
Different generations.
Well, they made a skate park to appease us, but the skateboarders, they made a separate park, but it's not Sadlands.
Okay.
Sadlands was just, originally they were trying to make a park that looked like the moon, so they built all these craters everywhere.
Yeah, so the
Yeah, you
actual
can
park.
probably find pictures of it online.
Okay.
But this is 80s and 90s. Back, they used to call it Sadlands. It was really fun. It was just a park, but it got totally, you know, skateboards don't exactly leave the surface as nice. Well, anyway, reminds me of Sadlands, okay? Or, since I am a skateboarder, there's another type of ramp in skateboarding called a spine ramp. Okay, and a spine ramp looks like this. You go up one side, you know, and you do a trick in the air or whatever, and you come back down the other side on the back. You've probably seen these, right? Lots of half pipes have them. Imagine a spine ramp that had a more curved look. So you could go up this side like that, and then down in the back like that. But the top is actually curved. So the reason I'm drawing this is because I want you to see something. On this first picture, whether you're traveling a red path, which is in the x direction, or a blue path, which is in the y direction, either way, the slope doesn't exist at that point, at that peak, okay? So this would be a case where both dz dx and dz dy are both undefined. In this picture, if you're traveling in the direction of the blue, right, you find a cusp here. There is no dz dx, you could say. But if you're traveling, if you're grinding the surface of this thing, if there's a metal pipe on here and you're grinding across, it is smooth, and it's because you're going in the y direction. So here you can see that the blue curve has a cusp, but the red one doesn't. Either way, I would still say that that's a relative max, see? So relative max will occur when either it's a smooth thing on top and both derivatives are 0, or one or both of the derivatives are undefined. So hopefully the skateboarding analogy can help you see that. If not, you can just memorize this, and if you can't visualize it, you can still do quite a bit with it, right? Okay. What about relative minima? Relative minima. I'm not going to rewrite a whole sentence for this, okay? AB will be a relative minimum, what? If ZAB is what? Less than or equal to all the ZXYs for all XYs in its neighborhood. I don't know if there are any relative min on this graph I've drawn. And your graph probably doesn't look quite like mine anyway, but maybe this point. AB might be a real min over here. If you draw a little neighborhood around there, maybe he's the lowest point around. And, you know, water tends to collect in these lower points, you know, which is a good thing. That's why we have lakes. Lakes are good. Right? Okay, any questions? All right. So this becomes then our tool, right, for finding these points. Knowing that both derivatives are 0, well, we take the derivative set them equal to 0, right? That's how we find them. One last comment on this first condition. If dz dx and dz dy are both 0, you could technically abbreviate that by writing this. the vector dz dx comma dz dy is the vector 0, 0, correct? And there's a name for this thing on the left. What is it called? Grad f. So if somebody writes grad f is 0, what they're saying is exactly this. Both derivatives are 0. Okay? Does that make sense? All right. Now, I said that a rel max occurs only when it's the highest point around and one of these two conditions are met. Don't try to take this 2 backwards, okay? If you find the derivative of 0, that does not mean you're at a rel max. You know that from 2D. You don't just take the derivative set equals 0 and say, oh, that's my maximum. No, you test it, right? This is the hardest part by far of 2D/3D stuff. Testing. Getting the critical points is easy, okay? Getting the critical points is pretty easy. Testing them is the hard part. Okay, so let's do an example now. Okay, and I think it all makes sense to you. The function I've chosen is from the Larson textbook, although I modified it a little. And the function is fxy equals 4x squared plus y squared times e to the 1 minus x squared minus y squared. So that's kind of an ugly function, but it has a really like complete graph. Like it's got all sorts of interesting points, okay? All right, so what would you do? You just take the derivative. By the way, I'm not a big fan of dz dx. I don't even like the Leibniz notation. I'm just going to use f sub x. It means the same thing anyway. What's the derivative? Well, it's a product rule, for sure. And you do treat it like a uv sort of thing. So u prime would be 8x. And actually, that's it. You're not supposed to do anything with the y's, remember? And then you multiply by v. Plus, and then we need v prime times u. Let me give myself a little more room here. V prime would be negative 2x e to the 1 minus x squared minus y squared times u, 4x squared plus y squared. And if I was just going to plug numbers into this, I'd leave it, but I do need to eventually take a second derivative. This is when I want to study the concavity, I'm going to need to do a second derivative eventually. So I think I'm going to go ahead and factor it real quick. Let's pull out the e to the 1 minus x squared minus y squared. And you basically get 8x minus 8x cubed minus 2xy squared. Okay? You take my word for it. So hang on to this guy. This is fx. And we're going to set him equal to 0 to find the critical points. So let's set that equal to 0. We get e to the 1 minus x squared minus y squared times 8x minus 8x cubed minus 2xy squared equals 0. But if a product is 0 and one of the terms is exponential, then it's going to be the polynomial's fault, right? So this is the expression that's 0. Okay, so hang on to this for a minute. 8x minus 8x cubed minus 2xy squared equals 0. Maybe you could factor out a 2x or something if you want to. Okay? I think I'll just leave it. So now let's look at dz dy. Might want to draw a big line here. First calculation is done. Okay, dz dy is again product rule. We can call it fy if we like. And it's 2y e to the 1 minus x squared minus y squared plus 4x squared plus y squared e to the 1 minus x squared minus y squared times negative 2y. Okay, that's again u prime v plus v prime u, but this time I'm treating x as a number. And let's factor that as well. So e to the 1 minus x squared minus y squared, and factor out that thing, and you have 2y minus 8yx squared minus 2y cubed. And if we set this equal to 0, like we did the last time, remember the peak of the hill most likely has both derivatives equal to 0, right? You can just treat this part as equal to 0. So now we have this statement. Now we wanted both of these purple statements to be true at the same time, right? we don't want only one derivative to be 0. We want both derivatives to be 0. So this is kind of the hard part. How are you going to get the roots of these expressions, right? The common roots. So you can do that. If you set them equal to each other, you will have two variables. Honestly, I'm going to be frank with you. You can guess every one of the answers. If you make x and y both 0, this works. If you make x 1 and y 0, they both work. If you make x negative 1 and make y 0, they both work. If you make x 0 and make y 1, they both work. If you make x 0 and y negative 1, they both work. Okay, most of the time, the author of the problem doesn't want you spending a lot of time on this. So you can probably guess all of the answers. I found 5 xy pairs that make this true. Then I went back and I went and solved it like formally, and I got the same answers. Okay?
How do you solve the form?
Well, the way I did it was, I took the two expressions. I'll copy my work down, okay? So what I did was I said, since f of x was 0, and that gave us this purple statement, it had the other thing in front of it, but I'm not needing it because that's the exponential. I pulled out a 2x like this, and I got 4 minus 4x squared minus y squared equals 0. Okay? I looked at it for a minute, and I thought, I don't think I can factor that. Let's move on. And then I wrote, for fy equals 0, I noticed I could factor that thing too. Only this time I could pull out a 2y. And it's 1 minus 4x squared minus y squared equals 0. On the first one, I noticed that this would basically just mean that either x is 0, right? That's one possibility. Or y squared is 4 minus 4x squared, right? So I just decided I said y squared. So either x is 0 or y squared is 4 minus 4x squared. On this second statement, which was my second partial derivative, either y is 0 or y squared is 1 minus 4x squared. Okay? So then I said, all right, well, I can take the x equals 0 from my first fact and plug it into the second fact over here. Okay? If x is 0, I can plug that into the whole y squared equals 1 minus 4x squared thing. So imagine taking x equals 0 and plug it in here. If x was 0, this would just be y squared equals 1. So y is plus or minus 1. So I'll write that at the bottom. If x equals 0, y squared equals 1 minus 4 times 0 squared. In other words, 1. So if x is 0, y is plus or minus 1. Right? Or conversely, so I just basically followed this red arrow. Or I could take the y equals 0 and plug it into the y squared equals 4 minus 4x squared. I could do that. So I'll show my work in red for that one. If y equals 0, y squared minus, or equals 4 minus 4x squared would look like, 0 squared equals. And from this, I get y equals 0, x is plus or minus 1. And then, of course, there's the possibility that x and y are just plain both 0, and that works too. If x equals 0, y equals 0, then both derivatives are 0. That was just more of an observational thing. I just noticed that right away. So here are the points I'm getting. X, Y pairs. These are all my A, B candidates for rel max, rel min. 0, 0 for sure. 0, 1. 0, negative 1. 1, 0. And negative 1, 0. Now you might ask, Mr. Why didn't you plug the x equals 0 into the y squared equals 4 minus 4x squared? And I'll just be honest, I don't think it's very meaningful to take two possible root candidates and try to substitute them together. I don't see why you would want to do that. So I just kind of cross-substituted there. But these are all values you can very easily check. Go back to these two purple expressions. Look at them. If x and y are both 0, they're both true. If x is 1 or negative 1, they're both true when y is 0. And if x is 0 and y is either 1 or -1, it works. So it might be a challenge to get these candidates, but most of it you can get by guess and check, if not all of it. And if you think there's more, you can attack it like I did, try to substitute some things. Okay, so now the test. This is the hardest part of the lesson. These guys, listen, are the only candidates. They are critical points. Let's label that. Let's label that. And I haven't written down their z-coordinates yet. We can do that later. We'll get the z-coordinates later. Okay? But these are the critical points. Okay? Does everyone understand that? If the function has maxes and mins, they are in this list. This is exactly what we did back in chapter 4 when we did Calc 1. AB stuff. Okay? Does everyone understand that this is it? These are the only candidates. Now there are no borders to this curve, like there's no like boundaries. So we don't have to go out there and test the boundaries. Remember how on a function in xy, like if you have a function like this, and you section this off, and you look at just this blue part, your rel max might be a critical point, or it might be an endpoint, right? We do not have to stress about that at all here, because this graph has no endpoints. It goes on forever. The second worksheet, the bonus one, is where I put in the endpoints. Okay? So don't stress about it today. This is just, these are the only candidates. How do you test them? How do you know which is which? Remember, when you're doing 2D, right? You might have a derivative of 0. Does that mean it's a rel max? No. It could mean it's a rel max, right? Or it could mean it's a what? What's another possibility? A rel min? Or it could be a what? That's right. It could be a point of inflection, specifically one that's kind of flat, you know. You know that, so we naturally would not want to guess at all here. We need a test. Now let me ask you, back in the world of 2D, what were some of the ways that we would determine that x equals a was a critical number giving us a relative max? Can you guys give me some methods we used back then? Because I think we can steal those. How did we know that this was rel max? The sign chart?
Yeah.
The sign chart, is, most of us like to use probably the F prime sign chart. It tells us if it's a positive derivative on the left and negative derivative on the right. That would be proof that this is a rel max, right? What were some other ways? If you gave it to a 7th grader and said, hey, prove that that's the highest point, what would they probably do?
Put the numbers with X
Use the sign, use the test.
I think they would test 3 points. They would find the y coordinate of this one, right? He's the candidate for King of the Hill. They would also test 1 point on each side, right?
Oh, yeah.
So they would test 3 points. They would say, well, I'm going to test point on the left, point in the middle, point on the right. A calculus student knows better than that. Calculus student knows, don't do that. We'll just take the derivative on the left, derivative on the right, make sure it goes positive, negative, right? That requires 2 test points, 1 on the left, 1 on the right, but not the point itself. Does anybody remember the fastest way to determine that this is a maximum?
Visual.
No. That doesn't prove anything. How can we use the second derivative?
If that equals
Concave down, right? The cool thing about the second derivative way of doing it is if you just study x equals a by itself and the curve is concave down, see? That's proof it's a rel max. You found this point by making the first derivative 0. Then you showed that the second derivative is negative. That's proof it's a rel max. We can use something similar to that in the surface world, okay? Because it's the fastest of those options, you see. Here's the rule, write it down. Let D equal fxx fyy minus fxy squared. That guy's ugly, but he's actually pretty easy to remember. He's like your discriminator, okay? He will tell you what kind of points each of these are. Okay? Now, if you take your A and B, right, you plug them into the second derivative, partial derivative with respect to x, second partial derivative with respect to y, multiply them together, subtract off a mixed derivative, you can actually use fxy or fyx, they're usually the same anyway, the square of that. Then that will give you a number. And that number will tell you what kind of point it is. Okay? So here are the possibilities. You work it out, and D is positive. Okay? If D is positive, and F double prime is positive, then AB is a rel min. Okay? If D is positive, and F XX is negative, AB is a rel max. Now before you freak out, okay, because this is pretty intimidating, we saw this before. When the concavity is positive, it's at the bottom. When the concavity is negative, it's at the top. That's the FXX. So that jives very well with our two-dimensional stuff. Right? Concavity positive, concavity negative. Okay, that's good news. And the D is greater than 0 thing, that's a subcondition. Actually, that's a primary condition. The subconditions are those FXX. There's another possibility, and that's that D comes out just completely negative. Which probably means it's a neither, right? Well, what kinds of neithers do we have in two-dimensional world? We don't really have inflection points anymore. Think about it. We don't have inflection points anymore, do we? We have saddle points. Saddle points, which is exactly what it sounds like. Okay? Let's practice drawing a saddle. Everybody draw a curve like that. Everybody got it? Draw another curve like that. Maybe not quite as curvy, but going down. On the left, connect with the bulging curve there. And on the right, do exactly what you just did. Make sure it's curved the same way as the left side. You can finish up your saddle here. You can put this on your favorite horse or donkey or whatever, okay? Why the heck are we talking about saddles? Here's why we're talking about saddles. When you sit on a saddle, you naturally sit at the minimum point on the saddle. But is it really a minimum point? It depends on what you're looking at, okay? You'll notice that when you're sitting on a saddle, right, and you look in front of you, there's that little part that rises up from between your legs, right? This little knob you can hold on to if you're riding a horse. You know what I'm talking about? You know how to ride a horse? Okay. If you look behind you, you see the saddle rises up behind your bottom, right? But if you look left and right, you're actually sitting on a peak. Your legs are hanging off to the side, which means you're on top of something. So there's kind of two perspectives here. If you look at this green curve, that red dot is a minimum, you see. But if you look at this blue curve, it's a maximum, exactly. And that's a saddle point, you see. Does that make sense? The red point is very interesting because both dz dx and dz dy are both 0, right? But it clearly is not a max or a min. It's kind of a hybrid point. This is sort of one of the weird cases that happens only on a surface. But you can easily find out its saddle point if d is negative. Now, I regret to inform you that if d is 0, this test is inconclusive. That's right. You gleaneth not a thing. Okay? And that is very frustrating because d is honestly quite hard to get in the first place. If this happens to you, and I promise you I won't let it happen, okay? I won't let it happen. But if it does happen to you, just know that you're going to have to do some z testing to see who's got the biggest z around. And you might have to convert everything to cylindrical coordinates so you can capture all the points in the neighborhood all at once. I think that's too much for us, and so we're not going to do it. My problems have d not being 0, okay? Let's go back to our problem at hand. So this is our brand new test. What's the point of this test? Why did we learn this? Yeah, we don't know what we just found, whether it's a rel max or rel min, right? Okay, the rest of this work, I'm just going to blaze through it, okay? Here's what I have to do. I have to find the second derivative with respect to x. I have to find the second derivative with respect to y. I have to find the d dy of dz dx, that's called the mixed derivative. And then I need to square that. There's a lot of work I need to do on my end. Let me pause the video. Okay, so the rest is kind of you copying down some things that I've already worked out the details of, okay? So I worked very hard on this, and I found that the second derivative with respect to x, I'd use the product rule again, is e to the 1 minus x squared minus y squared times negative 40 x squared plus 16 x to the 4th plus 4x squared y squared plus 8 minus 2y squared. Okay? And fyy, this is the second derivative with respect to y, partial derivative, is 1 minus e to the 1 minus x squared minus y squared times negative 10y squared plus 16x squared y squared plus 4y to the 4th plus 2 minus 8x squared. And I found the mixed derivative. Mixed derivative just means, basically means d dy of fx. So the first time I took the derivative with respect to x, treating y as a number, and now I'm d dying that. So I'm going to treat all my x's as numbers. Okay? And for that one I got e to the 1 minus x squared minus y squared times negative 16xy plus 16x cubed y plus 4xy cubed minus 2x. You don't want to see the details of this. You know how to take a derivative. It's a pain. Okay? It filled half a page for me to get that. Okay, so here's basically what I did then. I have this little guy called d, and don't confuse this with du from the other lesson. That was the directional derivative. This is our discriminator. His job is to find out what kinds of points these really are. So I started with 0, 0. 0, 0, which means I did fxx measured at 0, 0 times fyy measured at 0, 0 minus fxy measured at 0, 0. And for this, I got the number 16e squared. Now, is that positive or negative?
Positive.
Positive. Okay? I'll show you my values that I got, by the way. This was 8e, this was 2e, and this all came out to 0 squared. You can check my work later, okay? But you'll notice that d came out to be positive, 16e squared, right? And look at fxx. Look at fxx. I got 8e. Is that positive or negative? Positive. So you're actually supposed to look at two things. What did d come out to be, and what did fxx come out to be? They both came out positive. What does that mean? Look back at the rule. This was 16e squared. This was 8e. They're both positive. What does it mean? Relative minimum. Right. So that means that 0, 0, whatever the z is, I don't know yet, is a rel min. Is a rel min. Okay? What is the z, by the way? Well, you can plug that in. It's not too hard. It gives you 0, 0, 0. Okay? You'll have to plug it back to the original z function. Okay, then I went on, and I knew there were 4 more of these to test. So next one I did was 0, 1. And this time I got negative 24. Well, I'll show you just the work itself. I got 6 and negative 4 minus 0 squared. So this is your fxx, and the final result is negative 24. Now d came out negative this time, negative 24. But fxx was 6, positive, right? Yes, it's a saddle point, that's right. So the point 0, 1, and I actually found out it's 0, 1, 1, is a saddle point. I actually didn't really need to look at fxx, did I? As long as d is negative, it's automatically a saddle point. Okay, and then I tried 0, negative 1. This time I got 6 times negative 4 minus 0 squared again. So exact same result. This is the same as the last one I did. So my conclusion is that 0, negative 1 and the z-coordinate turns out to be 1, is also a saddle point. Saddle point is 2 words, by the way, not 1, sorry. Okay, and then the next thing I tried was negative 1, 0. And I got negative 16 times negative 6 minus 2 squared, which is 92. So D is positive. Look at your fxx though, that's the first thing I wrote, the negative 16. If D is greater than 0, but fxx is negative 16, this shows us that our point is a rel max. This is our first rel max that we found. It's at the point negative 1, 0, and I plugged it in and I got 4. Negative 1, 0, 4 is a rel max. And lastly, 1, 0. I got negative 16 times negative 6 minus negative 2 squared, but that still comes out to 92. And I have the exact same conclusion. D was positive, but fxx was negative, and this point, negative 1, or excuse me, positive 1, 0, 4, is a rel max. Now you might say, where are you getting the 4 from? I just got the 4 by plugging 1 and 0 into the original function. I need to save a little time. My whole goal is to get the concept across, and I'd like to show you the graph, okay? If the computer will obey me, computers sometimes struggle a little bit with graphs like these. I don't know, just so I can find it easily. I believe this is the function. Well, this might be a little hard to display.
Hey, I see some bumps.
It's kind of hard to get a good angle on it. Zoom in one more time. And let me change the pin width a little. Let's do more divisions. Let's do 72. Hopefully I don't lose my graph here. Sometimes if you do too detailed, you can lose it. But it's kind of hard to see, but I want to show you real quick. Listen. There's 2 peaks right here. Okay? There's 2 peaks right here. You can't see the surface too well, but it bends upward just slightly here. And there's a divot right in the middle. That's your 5 points. Okay? There's some saddle points too, but
Wait, aren't those two the one?
oh, excuse me.
The two on the sides are.
Yeah, these 2 are saddle points right here. Because they're minimums if you look this way, and maximums if you look this way. So there's 2 saddle points in here, and 2 peaks here, and a minimum in the middle. Very cool graph. It's a little hard to display with wind plot. But you can type that function into alpha, and it does a nice, no, not alpha, use an online plotter. Find an online plotter. Second lesson will be a video bonus, okay?
Do tomorrow if we do it?
No, none of it's due tomorrow.